So let's talk about cost terms and behavior. This is covered in Horngren chapters 2 and 10. It's also going to be in Wedgwood chapter 2. I'll talk about that in a separate video. And you'll also have an ethics discussion about this in your communications section. So the first thing we want to talk about are inventoriable versus period costs. And inventoriable costs are everything that happen in the factory. Every cost in the factory is an inventoriable cost. And we use absorption costing that's required under GAAP. It's called absorption costing because it absorbs all of those factory costs into the cost of inventory. And when you have all of those costs put into the cost of inventory, we call that full absorption costing. Everything has to be classified as a direct material, a direct labor, or a manufacturing overhead. So if you stop and think about what's going on inside the factory, if it is something that you can physically identify as part of the product, then it is a direct material. So let's say that we are making muffins. If you look at the muffin, you can tell that there is flour and eggs and blueberries and sugar and probably some baking soda. You can look at the recipe. All of those things are direct materials. The little paper cup that it is in would also be a direct material. And of course, the labor of all of the people that mix those muffins up and put them in the muffin tins, that's all direct labor. So direct labor are the people whose job it is to directly touch the product. And then everything else is manufacturing overhead. So the depreciation on the machines, maybe they spray the pans with oil to keep them from sticking. You can't really tell how much oil is going to be used. It's not part of the recipe. That may change from time to time. So that would be an indirect material, which is part of manufacturing overhead. If you have a janitor in cleaning up the warehouse or cleaning up the kitchens, that would be indirect labor, which is also part of manufacturing overhead. Taxes and insurance, all of those things are part of manufacturing overhead. If it takes place in the factory, it's either direct materials or direct labor. If it's not one of those two, it's manufacturing overhead. Now, if it doesn't take place in the factory, but it takes place in the rest of the company, then we call it a period cost. These are non-factory costs: selling, marketing, administration. They're usually expensed, and we talk about these as being period costs and expensed immediately, but sometimes we capitalize them. It's just never going to be capitalized as inventory. When you add those costs onto the full absorption cost, you end up with full cost. So full absorption cost is direct materials plus direct labor plus manufacturing overhead, and full cost are all of those plus the period costs. Now, if I have a computer in the factory and I capitalize that and depreciate it, that depreciation is manufacturing overhead. If I have a computer in the sales office and I capitalize it and depreciate it, that depreciation is a period cost. Okay, very important concept, but let's move forward. So the next concept we need to get down are direct versus indirect costs. Typically, direct costs are direct materials and direct labor, otherwise called our prime costs, but traceability is the key. Typically, we're not going to worry about tracing an immaterial cost because there's no cost benefit. The benefit doesn't outweigh the cost. So for example, the oil that we're spraying on those muffin tins. Now, we're not going to try to figure out exactly how many grams of oil are used per muffin on average. It just doesn't make sense to do that. It's easier to throw the cost of the oil into the manufacturing overhead. On the other hand, if we're in a roboticized factory and there is a robot that is programmed to spray exactly a certain amount of oil into the pan and is going to do it exactly the same way every time, then that's traceable. That would become part of the recipe or the direct materials list. It's traceability, right? Though that's the same example, but it's traceable in one case, not traceable in the other. That's because technology makes some of those previously untraceable costs traceable all of a sudden. The other thing is manufacturing cells. So it used to be in a typical manufacturing firm that you had a production line where people were working on, say, let's say that they were mixing those muffins, and then they went to a different person, and that person would pour the muffins into the different muffin tins, and then it would go to a baker, and the baker would bake the muffins. And those people were direct labor, but they didn't do anything except direct labor. In a just-in-time manufacturing environment, they have started doing product manufacturing cells where you have, say, three people, and those three people are responsible for mixing the muffins, putting the muffins in the muffin tins, baking the muffins, and then cleaning up their area, washing whatever leftover dishes there are, maybe sterilizing everything, maybe repairing something if it needs to be repaired, and doing a little bit of inventory management. And then they go back to making muffins again, and all they do are muffins, but they're also doing those other things. Well, all of a sudden, that indirect labor that was not traceable to a particular product, the night janitor came through and cleaned everything up, and the dishwasher washed the dishes from all the different product lines, that wasn't traceable. That was part of overhead. But now we can trace it because the people that are doing it and the supplies used to doing it are only used in that one little cell. So that becomes a traceable expense. So traceability is the key of whether it is direct, traceable, or indirect, not traceable. The cost object also changes traceability. So if I'm trying to trace a cost to blueberry muffins versus angel food cake, then the cost of the electricity in the building is not traceable. We can't figure that out. That's going to have to go into overhead. But if I am trying to figure out the cost of the Peoria, Illinois plant versus the Sioux Falls, South Dakota plant, then the electric bill is traceable to those individual plants. If I have a manager that's overseeing both blueberry muffins and angel food cake, I can't trace his or her salary to one product or the other. But if I am trying to cost baked goods, then that supervisor's salary is traceable to baked goods. Cost drivers are the thing that drive the costs, okay? So what we're trying to figure out is what is going to make our costs go up. Now, it should have a logical connection with the costs incurred. A lot of times, units of production are the thing that drive the costs. In other words, if I make another dozen muffins, I need 2 more cups of flour. If I make another dozen muffins, I need 20 more minutes of oven time. I need 5 more minutes of mixing time. The making more muffins drives those traceable or direct costs pretty clearly. But what about the overhead? What about the untraceable costs? And that's the big question. Tracing the costs of direct materials and direct labor to a cost object is not difficult. Figuring out how much electricity that batch of muffins consumed is a little bit more tricky. We want to figure out what is driving that cost. There should be a logical connection. And then we want to verify the suitability of that cost using regression analysis. Traditional cost drivers that we've used in the past, units of production for direct materials and labor, like I talked about, usually direct labor can be used. And so in your textbook, direct labor is frequently used as a cost driver. We can use direct labor as a cost driver for direct materials, even though direct labor doesn't cause direct materials, because they co-vary. And so a lot of times we use direct labor also as the cost driver for overhead that is either immaterial or fixed. It allocates, and that's an arbitrary measure. There is no real causality there, but it may co-vary enough to work. Square feet might be a way to allocate things that are consumed equally in all places, like electricity, taxes, rent, insurance. So you look at how many square feet does the muffin department take versus how many square feet does the angel food cake department take versus how many square feet does the orange juice department take. And then you can allocate perhaps electricity, taxes, rent, and insurance with those things. Although maybe not, because if we think about it, muffins and angel food cake both have to be baked. Orange juice does not. So perhaps we need to pick a different driver for electricity and use taxes, rent, and insurance by square feet. Just need to think about what makes logical sense. If we're changing from one product to another, then there is this big setup. So let's say that we bake muffins on Mondays, and then we use that same production facility and we want to convert it to make angel food cake on Tuesdays. Well, what we need to do is we need to clean everything, we need to scrub everything, we need to change the temperature on the oven, we may need to change out the mixing bowls that we use, change out some of the equipment. We're going to get rid of the muffin tins and bring in the springform pans for the angel cakes. All of that takes time and effort, and then once it's set up, it doesn't matter whether we make 50 angel food cakes or 500, we're done with that. So all of the costs incurred in that process is one setup, and we're going to allocate that to angel food cakes. If we're talking about a purchasing department, it might be the number of purchase orders. It doesn't matter whether we're ordering $100,000 worth of stuff or $50 worth of stuff. It takes just as long to pick up the phone, place the order, type up the purchase order, and put it in the mail. So number of purchase orders would be a good way to do that. Number of employees for allocating human resources. So I have a human resource department. I need to allocate the cost. Now this, of course, is a period expense, and we're getting out of inventoriable costs, but we still want to allocate the human resource costs out for our full cost measures. Okay, so the next topic we want to talk about briefly is relevant range. Relevant range is the range of normal activity expected over some period of time. So if we're going to produce above that, we need to have additional capital investment. For example, let's say that you can bake 40 batches of muffins in one 8-hour shift. You can't bake any more than that because each batch of muffins takes 12 minutes. Now, if you want to make more muffins than that, you need to buy another oven. It's outside the relevant range. We can't predict costs beyond that level because we'll exceed our relevant range. The minimum we want to make in an 8-hour shift is 25 batches of muffins. If we don't make at least 25 batches of muffins, we lose our economies of scale, and all of a sudden we're applying overhead to so few muffins that they become $12 muffins. That's not going to work. So our relevant range in this case is 25 to 40 batches a day. We can also talk about a relevant range over a time period. So for example, if I'm trying to predict my costs, I can do that maybe over a year. But if I'm trying to predict how much it's going to cost me to make muffins 20 years from now, most of my estimates are going to be wrong. So we need to keep our time frame close. All costs are fixed in the short run. That means that today I can't change my taxes, I can't change my rent, I can't change my supervisor's salary. But they're all variable in the long run. I could decide I don't want to make muffins anymore, fire everybody, sell all of my equipment, and my costs are all gone. And costs change over time. So these are reasons why that relevant range also refers to a relevant time period. Now what I'd like to do is move over to Excel and review some linear cost functions, including variable costs, fixed costs, and mixed costs. So for linear cost functions, we're going to look at just a few examples. The first example of a variable cost. So in this example, it takes a half an hour to assemble a product. Direct labor is $20 an hour. So the direct labor per unit is $10. And when we write that as an equation, that is y equals 10x plus 0. And that's saying that the fixed cost portion is 0 and the variable cost portion is 10, and it will go up $10 for every unit that we make. So if we add some data to this, I've taken and added a formula that just multiplies the number of x's by 10. Now what we're going to want to do is graph this and see how that graph looks. Okay, so what do we know about this graph? It starts at the origin. If I make no widgets, my cost is 0, and it goes up in a linear fashion. In other words, it is a straight line, and the slope of that line is 10. Let's go on and look at a fixed cost. So rent is $3,000 per month. Y equals 0x plus 3,000. The slope of our line is going to be 0. That means it's going to be a flat horizontal line. The fixed cost is 3,000. Let's add some data to this. Okay, there's our data. You can see that it doesn't matter how many X's we make, how many widgets we make. The relevant range for this project is 0 to 1,200. We don't know if we can make more than 1,200 units without having to rent additional facilities. Okay, so here are just the two graphs side by side. Notice that they have the same dollar values on the y-axis and the same number of widgets on the x-axis. The fixed cost, it is a linear equation with a slope of 0. And the variable cost is a linear equation with an intercept of 0. That means that it has no fixed cost. Okay, what happens if we put these two together? Let's take a look. Okay, so if we add the two together, we have $10 labor per unit plus $3,000 in rent. That makes our equation y equals 10x plus 3,000. We can add some data to this again. Let's graph this, and there is our mixed cost. It has an intercept of 3,000 and a slope of 10. Let's look at all three of these graphs together. You've got your fixed cost, has an intercept of 3, and it is a horizontal line. And then you have your variable cost, has an intercept of 0 and a slope of 10. And your mixed cost has an intercept of 3,000 and a slope of 10. So essentially, if we just took this line and moved it over to this graph, we would end up with the same graph as we have for mixed cost. These results are relevant from 0 to 1,200 widgets. So let's just cover what we talked about in Excel very, very quickly. Variable costs begin at the origin. They are a straight line. The slope of the line is the variable cost per driver unit. Variable costs vary directly with the cost driver. So in the example that I have here, if I have 2 cost drivers, I have $1. That's 50 cents a cost driver. If I have 4 cost drivers, I have $2. That's 50 cents a cost driver. The unit variable cost remains the same, 50 cents a cost driver. It's valid only over the relevant range. And my example here is 50 cents of chocolate in each candy bar. So my equation is y equals 0.5x plus 0. For a fixed cost, it is still a straight line. It's a horizontal line. It has no slope. Total fixed costs remain the same. Doesn't matter if I make 2 candy bars, my costs are 1,000. I make 4, my costs are 1,000. I make 6, my costs are 1,000. The unit fixed costs vary inversely with the cost driver. I make 2 candy bars, $500 a candy bar. 4 candy bars, $250 a candy bar. 10 candy bars, $100 per candy bar. It's still valid only over the relevant range. My example here is $1,000 of insurance a month for my chocolate factory. My equation is y equals 0x plus 1,000. The mixed cost puts it together. It begins at the fixed intercept. The $1,000 is our fixed cost for insurance. It's still a straight line. The slope of the line is still the variable cost per driver unit, in this case 50 cents each. The total mixed cost vary directly with the cost driver. So if I have 50 candy bars, my cost is $1,025. If I have 100 candy bars, my cost is $1,050. If I have 200 candy bars, my cost is $1,100. That's 1,000 plus the number of candy bars times the 50 cents. Unit mixed costs vary inversely with the cost driver. So if I make 100 candy bars, that is 1,050 divided by 100 gives me $10.50 a candy bar. If I make 200 candy bars, I take that 1,100 divided by 200, $5.5 per candy bar. So it's going down. still valid only over the relevant range. This is my example, and my equation is 0.5x plus $1,000. Some of the assumptions we make with this: all costs can be broken into fixed and variable components. Variations in the cost driver explain variations in the related total cost. This doesn't always work. For example, if I have electricity in my factory, certainly if I'm cooking muffins and cakes, the amount of muffins and cakes I make is going to increase my oven time, is going to increase my electric bill, but that's not going to explain all of the variations. The weather outside can also affect, say, the air conditioning cost. So we're not always going to be able to use that. Costs behave in a linear manner within the relevant range. From economics, you know costs are actually curvilinear. But if you take a curved line and you slice a small enough chunk of it, it approximates a linear function. The relevant range is meaningful both in terms of quantity of output and the time frame. So that relevant range has to be both how many we're making and the time frame that we're making it. I want to do two more things. I want to go through the high-low method. On the screen there are a few points about the high-low method. Regression analysis is much more accurate. It takes all the points into consideration, but it requires some computer skills. So let's go back to Excel and take a look at both of these methods. In order to predict mixed costs, we want to break it into a fixed and variable component. We're going to start by using the high-low method, which is a very easy method to do on the back of an envelope while you're sitting at a restaurant discussing a business idea and you don't have a computer readily available. You can see on the screen we have our first set of data, and the first step in doing the high-low method is to see if you have a reasonable cost driver. So what we're looking at here is we have 10 weeks worth of data. We have put our predicted driver, what we think is our cost driver, into column B and the quantity of that. And then in column C, we have the actual costs that we've accumulated themselves. And we want to know, for example, is it true that if we use 206 of our drivers, that our cost will always be around $2,267? So the first step is to do a scatter plot. Does that look like there's a good linear relationship there? Is there a line we can draw through this that most of the points are close to? I don't think there is. There doesn't seem to be any relationship here at all. So what this tells us is that we've chosen a poor cost driver. Okay, let's look at another set of data. We still have 10 observations. We have our cost drivers and we have our costs. And so let's do that scatter plot again. This looks a lot better. That looks like there is a linear relationship. So we're going to look at this and try to solve the equation. So what we're trying to do is we're trying to come up with an equation that says y equals the variable cost, and remember the variable cost is the slope of the line, times x. X is our cost drivers, plus f, and that's our fixed cost. So there's the equation that we're trying to come up with, y equals vx plus f. The first step in this is to calculate the variable cost. You may be familiar with the idea of rise over run. Now what we need to do is we need to use the high and low values of the cost driver, not the dollars. So if we come over here and we look, we have our low cost driver is this one. It's series 0.1, 22,730. That is our low. So let's go ahead and highlight this and call this our low. Notice that this has got a lower dollar amount. There is a $680 amount, but we don't want that. We want to go from the lowest driver to the highest driver. Ignore the low and the high dollars. Just look at the low and the high driver for right now. So our high driver is up here. It is the point that is at 70 and 1450. So we're going to find that. Here it is, 70 and 1450. So those are the points that we're going to use. And then the formula is rise over run. We're talking about the change in dollars, or the change in the y-axis, over the change in activity, or the change in cost driver, the change in the x-axis. So when I put that down, I get 1450 minus 730. That's the change in the rise, or the change in the dollars, divided by 70 minus 22. That's the change in the cost driver. That equals 720 divided by 48, which is $15. That $15 is our variable cost. So now we've determined that the variable cost equals 15. We need to go in and calculate the fixed cost. So to calculate the fixed cost, we want to use the same points we used before, the 70 and the 22, so the high and the low week. We want to plug it into the y equals vx plus f framework and solve for f. So let's see what that looks like. So we're going to start out by taking the first point, 1450 equals 15, that's our variable cost, times 70, that's our driver unit from that high, plus f. And when we solve for f, we get 400. To double check it, let's put it into the second equation. We get 400 again. That means that our formula is y equals 15x plus 400. So we've solved this equation. Now what we want to do is a point estimate. So a point estimate is when we want to predict our cost for a specific activity point. In this case, let's look and see what happens when we have 45 drivers. Okay, we're going to have 400, that's our fixed cost. We're going to have a variable cost of 15 times 45. This is when we have 45 drivers. So our total cost then is going to be 1,075. That's our point estimate. So we just plugged 45 into the equation, 45x into the equation, and we got an answer. So there's more that we could say about the high-low method, but let's move on to regression analysis. Remember, in the high-low method, we were able to look at a scatter graph and get an idea of whether a cost driver had a relationship with the costs or not. But for a more rigorous or analytical way to do that, we would use regression analysis. And we want to take a look at some data now. The data is in Excel. Week 1 through 10 is the same as we used in the high-low example, and the costs are the same as we used in the high-low example. I took the cost driver and I have called that machine hours. It's in column B, and one manager thinks that machine hours are driving the costs, and another manager said, no, I think it's direct labor hours. And so we have gathered direct labor hours for weeks 1 through 10, and we'd like to do 2 regression analyses and compare the results and see which one is the better cost driver. We will use the results from that analysis to write the y equals vx plus f equation so that we can make point predictions, and we'll take a look at a point prediction. To start regression analysis, you want to come to the Data tab, and all the way over to the right, there should be Data Analysis. Now, this is not automatically loaded into Excel when you start the program, because not everybody does data analysis. So if it's not there, if you go to the Data tab up here, and there's no data analysis over here, then come back to the File tab, come down to Options. When you get to Options, go to Add-ins, and you want to go to Manage Excel Add-ins down here at the bottom, and make sure that Analysis Toolpack and Analysis Toolpack VBA are both checked, and hit OK. And then it should be up here under Data, all the way to the right, Data Analysis. If it's not, try closing Excel and opening it again and seeing if it's there at that point. So we're going to click on Data Analysis. We're going to choose Regression, so click on Regression and hit OK. And then it's going to ask us to input our ranges. So the first one it asks us to input is our Y range. Let's go back and look at that again. Input Y range. Click on the little red arrow, and remember that the Y is our dependent variable. It's the variable that we are trying to predict, or our cost. So we're going to select our costs and then click OK there. And now it asks us for the X range. The X range is the independent variable. It's the number that we're trying to use as our cost driver. Let's select machine hours and see how we do. Notice that I have selected in both cases the title as well as the numbers. So I want to go in and make sure that labels is clicked. If you don't have labels clicked, then you don't want to choose your label. We can tell it to put this into a new worksheet ply, or we can tell it to put it into an output range right on the same sheet. But let's go ahead and do a new worksheet ply. And we're going to just click OK. And notice that it came up here on a new worksheet ply. And I'm going to clean this up a little bit. I just made this wider so that we can read this. These first three numbers are actually percentages. And then I'm going to take all the rest of these numbers and just put them into comma format. So now let's just take a look at some of the things on this screen. The first thing that we're interested in is the R-square. The R-square is also called the coefficient of determination. And this tells us what percentage of the variance in our dependent variable is explained by our independent variable. In other words, how much of the cost we're trying to predict is explained by or driven by machine hours, and in this case 86%, and that is really good. 86% is an excellent R-square. Another thing that we want to look at is the standard error. This standard error is $95.17. That is telling us that when we make a prediction, it may be off by as much as about $95. We can look at the T-stat. Generally, a T-stat above about 3 is pretty good. The bigger the better. And for machine hours, the T-stat is 7.03. So that means those are both indicators that this is very good. Another number we want to look at is the p-value. P stands for probability. Is the probability that we got these results strictly by chance? Now, they look like they are 0.00, but there's always a possibility that this is strictly by chance. And if you come up here and you look at the p-value for machine hours in the formula bar, you can see that it is actually a 0.000109, etc. chance. So a very small chance, about 1/100th of 1% chance that this is all just random. That's an excellent p-value. Usually we talk about p-values that are at the 1% level, the 5% level, or the 10% level. So 10% of 0.10 would probably be the highest we would want that to go and still use the numbers. Okay, so let's write the equation. So when we're looking at our regression results, we're still trying to predict Y. Our variable costs are $14.22 per machine hour. That is our independent variable, and the coefficient of that independent variable is the variable cost per unit. Our fixed costs are the intercept, so 424.62. So there is our equation for predicting costs now. We predicted in the high-low video, we were predicting what would happen if there were 45 machine hours. So let's take a look at this. We have $14.22 times 45 machine hours. And our fixed cost, of course, is $424.62. And so the total cost is the sum of these two. So our predicted value is $1,064.52. Let's go back to sheet 1, which has our data on it. And we want to see if the other manager is got something with this direct labor hours. So let's do the regression again. We're going to come up to data, data analysis, regression, okay. Our Y range is the costs. Our X range, in this case, is going to be direct labor hours. We're going to say new worksheet ply, and it puts it onto another sheet. What are you seeing already as we're looking at this? Do you see any numbers that you can evaluate? What do you think about the fit of this? Well, let's start out with our R square. Our R square is saying that that direct labor hours only explains about 13% of the costs that we've incurred. So this is not very good. And the standard error is very large, $237. You can go down and you can look at the T-stat. Neither T-stat is over 3. So those are not very good. The intercepts p-value looks like it is okay, only about a 6% probability, but that is random. But the direct labor hours, 30% probability that it is strictly random. So this is a really poor fit. We can go back with very good comfort and tell the managers that no, in fact, we want to use machine hours. Let's go back to that tab. The machine hours, we have 86% coefficient of determination. We have T-stats that are good and strong. We have very low p-values. The last thing I want to do on this video is show you a tool or a choice that you have on the regression analysis that might help you understand what you're doing a little bit better. Let's do this one more time. We're going to go to data analysis, regression, okay. We never want to choose constant as 0. That forces it to be a strictly variable cost. It forces the intercept to be 0. If we knew we had a strictly variable cost, we wouldn't need regression to analyze it. I'm going to choose the output range in this box, and so I'm going to tell it that I want the output range up here on F1, and we'll see what that does for us. And then I want to check line fit plots, and let's see what we get here. I hit OK. Here's our regression. This is exactly what we had before, but let's look at the residual output for a moment. This is telling us that for observation 1, if we use the formula that we came up with, which was y equals 14.22 mH plus 424.62, I rounded that to pennies, then we would have gotten 1220.98. Our actual cost, you can see, is 1,090, and so there is a residual, there is a difference there. It's not a big difference. It's about 10%, okay? And you can go down and you can look at all of these different residuals. The last one is very close, right? It predicts 737, and we actually have 730, so it's only $7 off. This is also shown on this plot here. This is showing the orange squares are the predicted costs. So you notice that that is a nice line. The predicted costs are going to be linear because this is a linear regression analysis. It's forcing everything onto the line of best fit. If you look at the blue dots, those are the actual costs. And so we can see how far the actual costs are away from their predicted costs. So we can go up to this one, for example. This is 22,737. That's that one that we just looked at that is only about $7 off. And you can see that the orange dot and the blue dot are very close to each other. We can look at one that's further away here. Let's look at this one. So this is the predicted cost is $837 and the actual cost was $680. So this one is pretty far away. So something happened that week that kept it from being right on that plot. But this gives you an idea of the goodness of fit as well. Let's go back to our regression results and do a real quick overall review. The R-squared, the coefficient of determination, that tells us how much of the dependent variable is explained by the independent variable, or how much of our costs for the month are explained by machine hours, how good of a cost driver that is. We want to look at the t-stat, the larger the better. We want to look at those for each row of the regression. The p-value, the probability that these happened only by chance, that these results are strictly random. We can take our coefficients and we can use those to write our equation, and once we have the equation, we can use that equation to make a point prediction like we did here for machine hours at 45. So we've ended our video on cost, behavior, and terms. There is a worksheet on D2L for you to download and complete to make sure that you know all of the terms. Remember that everything in this video is fair game for the first exam, and that there is a Wedgwood assignment to do and an ethics discussion coming up. Thank you.